So let's have a little side of Haskell. And I've been talking about Haskell to this part of this forum several times already. So I hope the ones who are listening to it like the third time maybe already know some Haskell. How many people here know some Haskell? Yeah. 3, 4. 3.5. Okay. So in Haskell there is this data structure called maybe. Okay. That it's sort of very similar to unique pointer. It's just one aspect of unique pointer that it can be empty or not. Except that it just, so data may be A. That means I'm defining a data type, I'm calling it a maybe, and it is parameterized by type A. So A is type parameter, okay? And it can have two possible things. It could be, it either is nothing, right? Sort of like a null unique pointer, or it could just, but then just takes A as an argument, some value of type A, and hides it.
It's kind of like Sharp's nullable, right?
Like what? Nullable? Yeah, nullable. Option also. Some other languages called option. Yeah, it's a known thing. Yeah. So maybe is a functor, just like unique pointer is a functor. So that means that it has fmap defined for it, right? So so now I want to show you the declaration of fmap, right? The type signature of fmap, because this is where Haskell works very nicely with these type signatures. Fmap is a function. How do I know that it's function? Oh, I'm looking at these arrows at the top level, okay? So if I see arrows, I know that I'm talking about function, because it says from this type to this type. Now here are two arrows, one after another. So how do I interpret this? Okay, the simple way to interpret is that the last arrow points at the return type, and all the previous arrows just separate argument types. Okay? There's one way. We'll have another way for doing it soon. So fmap takes, the first argument is A to B. Oh, so the first argument is a function. Okay, so it takes a function, that's the function to be lifted, right? And it takes the second argument, which is maybe A. So it takes a maybe argument and returns a maybe value. Yeah, it's exactly like what I did with lifting there. And here's the definition. The definition is very simple, fmap f nothing. So when you call it with nothing, it will return nothing. And if you call it with just, then we'll just apply f to the inside. This is called pattern matching of the arguments. And it's the same function, but defined kind of using pattern matching magic. It's a very nice notation in Haskell. You get used to it so quickly. And compare this with unique pointer. There's also these two patterns, but they are done using if, which in Haskell could be done with if, but that would be not elegant.
Will Haskell warn you if you don't match every possible case? Or is it an error?
Huh?
It's an error.
It's an error.
Oh, okay. Interesting.
I mean, it depends on flags, right? To the compiler.
You mean otherwise, or default or something, but you specify it.
Oh, that's right. Yeah, you can always have the catch-all case if you want. So, what is it? So I showed you this definition of fmap, right? And you see the signature of this fmap is a function taking two arguments and returning a maybe, right? But before I was talking about lifting these functions, So you should take a function and return another function, right? Is there a difference between these two? Which is it? Right? It should be this. Take a function and return me a function. That's a very much nicer way of writing the same thing. But I said it, the same thing. It is really the same thing. And here's my function diagrams. Okay? About currying and partial application. Because this thing can be explained using these terms, currying and partial application. So let me explain that. So this diagrammatical way of looking at functions is, value is just no function. Function has a hole for the argument. Okay, so it's an arrow with a hole for the argument. If it's a function of two arguments, it has two holes. Okay? And function call is, you have an arrow and you have an argument. You just close the hole and you have a value. Very simple. Fmap is kind of funny because it's a function of two arguments, but the first argument is also a function, right? So I put a little arrow here. And we are putting, let's say, calling it with length and something, a here. Right? And notice that that's another graphical element. I put some kind of halo around it, meaning, okay, this is the value that's being encapsulated or enriched by maybe, for instance, in this case. And this hole also is shaped. It actually accepts a halo. The length is just a regular function. So if you fill these two, you get a value, right? Actually, this value should also be with a little halo, right? Yeah, okay. So, I was just going through these slides back and forth, adding new elements. We've got to go back to this one. Yeah, they both left-hand side here, and this should have a little halo. So currying is this. Okay? We have fmap with two holes. We provide both of these, and you get a value. Here you have fmap, and you curry it. It means you cleave it like this. And the cleaving means that it's really a function of one argument, but what it returns is also a function of one argument. Okay, so this is like the return value of the function. So now if you say fmap and you give it length, you fill this hole in, and you are left with the result, which is still a function, right? So that's the type signature like this. Okay, you give it a function, and we return you a function. And of course, this should be shaded. So in Haskell, once you get used to it, it's like normal. You have a function of 3 arguments. You just curry it, and you can fill one argument, second argument, and so on, and you get a new function, and so on. In C++, you can do that too. You have a series of library functions called a bind. They used to be called bind first, bind second, so on. No, I think they are all bind. So let's recapitulate the functor pattern. So a functor pattern is built on type of type constructor, which is a recipe to create a new enriched type from any type. And it kind of encapsulates height values from the underlying type. Lifting of functions, that's the recipe for taking a function and making it a function of enriched types. And this is represented by this higher order function fmap. It's a higher order function because it takes a function as an argument. The advantages of using fmap is that No need to break encapsulation as long as you just want to operate you have a library of functions that operate on normal values, and you suddenly introduce your new enriched values, and you would think, okay, now I have to rewrite the whole library to work on enriched values. No, you don't have to. Right? You have fmod, you just apply fmod. And they are composable, as I showed you. There are some functor axioms of composition and identity. I won't be going because of lack of time. These are interesting things. Yeah. So this is fmod. Okay, next stage. It's getting a little bit more difficult with every stage, right? There's something called applicative functor, and it's about applying functions to enriched values. I mean, yeah. So we had application of a single argument function that's called lifting function to work on a single argument function can be lifted using fmod, right? But what if you have functions of multiple arguments? It's a binary function, right? You have a binary function that takes, some type A and B, but suddenly you don't have A and B. You have unique pointers to A, unique pointer to B. Can we do the trick and lift this function of two arguments? And now that you know about currying, of course you can take a function of two arguments, say, okay, it's a function of one argument that returns a function, right? So if you lift it, you get a function that takes an enriched argument, but what it returns is an enriched function of one argument, right? The curry, the partially applied. Okay? So lifting function of two arguments, lift by first argument, right? So here's an example of concat. Right? And to do this this way, okay, you would have to curry concat. And you can do it by using this, well, here it's Haskell, so you don't have to do it, but in C++ you have to explicitly curry it. So this thing, so you end up with, as I said, an enriched function, right? So you have like something, and inside is a function, not just a old value, but good old function, right? So how do I apply an enriched function acting on an enriched argument? That's the second argument I have to use, right? So you define this new operation called apply, which does this. So here's the example of maybe. So here's a function a to b, but it's enriched by maybe. So that means that there could be a function or it could be nothing, right? And it's acting on some maybe a. So there could be an a or it could be nothing. And it should return maybe b. Now, because b is the type, the return. So how do you define? Okay, both of them have to be just. Otherwise, there's no application, right? So you have to have a function in your hand, you have to have a value, then you can apply. Right? So you just apply function to value, and you return a just of this stuff, saying, yes, I succeeded. This means pattern matching everything, right? So if this does not apply, then whatever other combination you have here of patterns, just return nothing. Which means if the first one is, the function is nothing, then who cares about the argument? If the argument is nothing, who cares about the function? It's still nothing. And if both of them are nothing, then you have nothing squared. So here's the signature of apply, and here's a picture of it. Nice. Okay? So apply takes a function, and it's a function of two arguments. Right? This kind of function. And it has two holes to fill. Right? Because this is a function of two arguments, but notice these are shaded, right? Enriched. Just look at it from the distance. Is this stuff enriched? So these are enriched A and B, right? And when you fill these two and this one, then you get everything filled and you get a value that also should be shaded, right? Because you get back an A. So pay attention to this notation because I will try to explain a monad using this notation and nothing else. Okay? So here's back to C++, okay? Applicative functor. Unique pointer is actually an applicative functor. Hey, you can define apply very easily. So apply takes this enriched function from A to B and a unique pointer of A. Okay, and result. And if both of them are not empty, same thing as we did in Haskell, okay? Both of them are not non-empty, then you can apply, you can get the function f out of the first one by applying star, get the value from the second one by applying a star, act one on another, right? And that's your new result. You return a unique pointer. Actually, you don't have to carry the function in this case. Unless you just follow whatever Haskell. This is actually non-Haskell way because it doesn't recur. And there's an alternative for languages like C++. That actually in Haskell this is an alternative too. That you can define these fmap2 operation in a very straightforward way, right? Take a function, take two enriched arguments, right? And then take a function, lift it, and then apply it to the first argument, and then, So here's the example of how you would implement fmap2. You have function f, enriched, p1 and p2. Right? Very simple. Is it correct? Yeah. The only difference between the previous one is that now f takes two arguments, right?
Also that,
You should include F in the test.
Yeah, you're right. Oh, sorry. Yeah, f, and this should, yeah, okay. I'll correct these thoughts.
Wait, why would F need to be lifted? I thought that only applied to apply, no pun intended. I thought the F map took this
Okay,
function.
yeah, maybe I shouldn't have agreed so quickly. I take it back. You're right. Yeah, f is just a regular function. No, actually, yeah, this code I took from an actual program, so. Be more confident. So here's a summary of applicative, right? So it defines the apply function, the higher order function, right? Enriched function acting on an enriched argument. But there's also something else that is required, and that's called pure. Pure is a way of taking a regular value and making it enriched. Okay, so there has to be something like this to call it applicative functor. Okay? And in case of unique pointer, well, that's trivial. Pure, give it a value of type A, it just returns a unique pointer of A. It constructs A. Right? So, pure sort of acts like instead of using, so if you have a function of two arguments acting on two enriched values, you can say, okay, let me first do a pure on this function, right? And now I have a function that's also, and then I can use a plot.
So why is it called pure if it's like enriching the time? Why is it called pure?
Because it's pure enriching. Doesn't do anything else, just purely enriching.
You think lift would be the right term for that?
No, lift is already taken. No, a lift. There is no function lift.
Well, you're defining a function. You're just talking about names.
You mean fmap? That's lifting functions.
Lift instead of pure.
Yes?
So with the pure, you're always copying, right? Is that?
By copying, you mean like C++ copying?
Yes,
And
an
you have to
object,
copy
it's a copy, a copy.
rather.
Is this sort of the general pattern that that's what you want? Is it a lifting and a clone?
That's left as an exercise to the reader. I haven't thought about it deeply, so I can't just really find a good answer. So the examples of these applicative functors are on the usual suspects. It's unique pointer, and vector, function, and many, many. And where it's used usually, at least in Haskell, people often use it to lift operators, binary operators, right? So you have class defined on your stuff, and now you say, okay, but I don't have my stuff, I have enriched stuff, so I have to lift. So, okay. And of course it has its implicative axioms, which I will not be talking about, but it's worth knowing that there is some, like, basic things.